Hey, our science class is a lecture on the ocean floor. So the oceans are huge. 71% of the Earth's surface is covered by the ocean. If you were like some sort of spacecraft landing on Earth in a random location, you're most likely going to crash into the oceans. Okay? Only 29% of the surface of the Earth are continents and islands. And you can see that in this image here, the different land areas and the amount of approximate square kilometers they cover. As you can see, here are the different oceans, the 4 major oceans. They cover a lot more square kilometers than land does. Here's the equator at 0 degrees latitude. And if you notice something, the majority of the land areas are in the northern hemisphere. The southern hemisphere really is dominated by ocean water. Okay. So if we were floating out in space, hovering above the northern hemisphere, we could refer to it as the land hemisphere. So here's the North Pole. If you notice, there's a lot of land in the northern hemisphere. If we were kind of underneath the Earth, but I mean, if you're in space, what's underneath, right? But if you're in this perspective, looking up at the southern hemisphere, yeah, this is mostly water. And there's Antarctica, but it's mostly water surrounding the southern hemisphere. So we refer to it as the water hemisphere. Okay, so there's 4 main ocean basins. It's all one world ocean because they're all connected, but we give them arbitrarily give them distinct names of their different basins, so we know, what you're referring to. Pacific Ocean is by far the largest. You could actually fit all the different land masses within the Pacific Ocean, which is pretty crazy. Atlantic Ocean is about half that size, and it's not as deep as the Pacific. The Indian is smaller than the Atlantic, okay, and then the Arctic is really small in comparison to the Pacific, about 7% size. So here they are: Indian, Atlantic, Arctic, Pacific Ocean, 4 main ones. Oceanographers give a distinct name to the area beyond about 50 degrees south of the equator, the Southern Ocean, because there's distinct properties of the ocean water there. It has to do with ocean currents and the west wind drift, but the Southern Ocean really is portions of the Pacific, Atlantic, and Indian. All right, so what's bathymetry? Bathymetry is the measurement of ocean depths, understanding the topology of the ocean floor. For the longest time, we had no clue. We had no idea what was in the abyss of the ocean. Today, we have a lot of technology to be able to map the bottom of the ocean floor. And to our surprise, there's a lot of features down there. Okay, it's basically bathymetry is understanding the shape, the topology of the mountain ranges, the valleys, and the trenches that we find in our varied ocean floor. So look, this is a bathymetric map of a subduction zone, and here's a deep ocean trench. These are the deepest parts of our ocean. Okay, so the way this kind of began really was with eco-sounding. Prior to eco-sounding, the technology to determine the depth of the ocean floor was by throwing line overboard and seeing, with a weight on it, and finding out how far or how much line it took to get to the bottom of the ocean floor. Later, because ships were running into icebergs, that was a big deal. Eco-sounding was developed because it's basically like sending out a sound signal away from the ship, and initially it was done kind of parallel to the sea surface because the ships would do it ahead of them so that they received, if the sound waves bounced off something in the distance, it reflected back towards the boat. That would indicate that there's something there in the way, most likely an iceberg. So that's what they used it. But then later they kind of pointed it downwards. And so if you send an outgoing signal downwards, it'll travel all the way until it hits the sea floor, and then it'll bounce back. It'll be a reflected signal. Then you can have a receiver collect that signal. And if you know the time it took for that signal to travel down and bounce back, it moves at a constant velocity, and that velocity is determinable, then you can actually find out how deep the distance is to the seafloor. So that was quite useful in finding out the depth of the seafloor, because that helped understand or let ship captains know where to navigate without running your ship into the seafloor. As technology improved post World War II, Sidescan sonar, multi-beam sonar were developed. Okay, and essentially it's an array of sound sources and listening devices. So it creates like a swath of information that like hits the seafloor and comes up and is received by the ship. Okay, I think I have an image in the next slide. And then later on, once we had satellites have altimeters, and altimeters can measure the shape of the ocean surface, measure small, really small anomalies in the sea surface, which can determine major features of the seafloor. Okay, so here is the Sidescan sonar and multi-beam sonar, and essentially you'd have to kind of ride your boat and then turn around and overlap this area to produce a very detailed map. Sidescan sonar and multi-beam sonar, you're able to resolve really small features on the ocean floor. Like you could find shipwrecks or really small distinguishing features of the seafloor. Only about 5% of the ocean floors are mapped in this detail. 5%, that's it. It's a lot of ocean out there. And they help develop really detailed maps like this. The continental margin off the coast of California. Here's Long Beach. Here's the continental shelf, and we can see that it's flat all along these areas, and then there are these huge canyons here and really steep slopes. So that was pretty amazing when these places were initially mapped. Here's a satellite. Here's a radar altimeter, sends down a signal, and we can determine small little anomalies on where the sea surface is supposed to be versus reality. Okay. And what happens is when there are major features on the ocean floor, like mountains, giant seamounts, or plateaus, that adds a little extra gravity into this area, and what happens is water piles up on top of these major ocean features. So if we see that sea surface anomaly, you can basically reconstruct what's going on underneath the seafloor. So satellites don't map the ocean floor directly, they just kind of distinguish small features on the ocean surface and then project them down to what's on the seafloor. And that's why when you get on Google Maps and you can go into like satellite view, you can basically see the entire ocean floor and all the major features, which is very impressive. Okay, so after all that detailed mapping with Sidescan sonar, and then the use of satellites, three major topographical units or regions were discovered in the ocean floor. There are continental margins. Okay, that's where continental crust and ocean crust kind of intersect, let's say, or it's where the shoreline is, and a few interesting features are there. Then there's the deep ocean basin floor. Okay, a little further out from the continental margins, and then when you go past the ocean basin floor, you'll run into mid-ocean ridges. Okay, and mid-ocean ridges are that divergent plate boundary where ocean plates are being created. Okay, so let's take a look at the Atlantic Ocean basin. It's very satisfying because it's symmetrical. Okay, we refer to this as a passive margin. Okay, our margin, the East Coast margin of the United States and the West Coast margin of Africa are pretty far away from tectonic plates. So the boundaries of tectonic plates. So here's the divergent plate boundary. They're pretty far away from each other. Here's another boundary. Okay, but that's still considered pretty far away from the East Coast. Okay, and so what do we see here if we go from Massachusetts all the way to Morocco? I don't know what country's over here, but we've got a continental margin. Here's on the East Coast of the United States. We have a continental shelf, relatively flat area. Most coastal waters are found here. Then there's an abrupt decline in the topology, and we call this continental slope. Then there's a big wedge of sediment called the continental rise, and this bleeds into the deep ocean basin, and these are the abyssal plains. really flat, deep areas of the ocean floor. Okay, and then actually the topology changes and it begins to rise. Okay, it rises all the way up these different ridges and valleys until the apex here of this rift valley. This is the mid-ocean ridge. So this entire area here is considered the mid-ocean ridge. They're raised areas of the ocean floor. Okay, they're at a higher elevation than the abyssal plains. And at the center of the mid-ocean ridge typically is a rift valley, a low-lying area where all the volcanism occurs. So a bunch of pillow-basalt eruptions occur there at the bottom of the ocean. And then as we approach Africa, this descends down into lower and lower depths back into the deep ocean basin and the abyssal plains here. And then we ride up the continental rise, big wedge of sediment, continental slope, and back over to the continental shelf on the African side. So it's really nicely symmetrical right along the middle of this ocean basin. And these two margins on the east coast of the United States, west coast of Africa, are considered a passive margin. Okay, passive continental margins are found all along the east coast of the United States. They're far away from plate boundaries, which means there's very little volcanism, if any, and very few earthquakes. That's nice. Okay, so here are the typical features you'd find on a passive continental margin. Okay, this is the shoreline. Okay, and here's the continental shelf. This whole area here, relatively flat area. This is where our coastal waters are. Essentially, it's a portion of the continent. It's just temporarily flooded by the ocean. Sea level rises and falls, and when it rises, it just floods a larger portion of the continent, and that becomes part of the continental shelf. And when sea level falls during colder times, glacial periods on Earth, there's a not as wide of a shelf. Okay. And then this leads to this steep slope here. Okay, there's a huge drop off. The angle of drop off varies a little bit. And then here, this area here is the continental rise. This is where a huge wedge of sediment is deposited in this flat lying area that leads into the abyssal plain and the deep ocean floor. Okay, so the continental shelf is kind of varies widely in width. In some areas on the East Coast, it's pretty wide. Like, let's take Florida, for example. The west coast of Florida, its shelf is much wider than the East Coast. Okay, so it really depends where you are. It's not perfectly flat. It is gently sloping towards the mid-ocean ridges. And these areas are important fishing grounds. It's all our coastal waters. And because there's a lot of sediment that's derived from continents that's deposited on the continental shelf, they contain a lot of oil and other important mineral deposits. Okay. Some areas are covered in glacial deposits. Earth has been much colder than it is today. We've had a lot of continental glaciers on land at lower sea level. So then a lot of glacial related deposits have been found on the continental shelf. Okay, so here's a to scale cross section of the continental shelf. So it looks fairly flat here, but it is dipping towards the deep ocean. Okay, the slope is the seaward edge of the continental shelf. Here it is. Here is the slope. Okay, it's a steep structure. It's the boundary between the ocean crust and the continental crust, right? Right at the end of it, here's the ocean crust, and this is the continental crust. Okay, it can vary between 5 degrees of sloping to about 20 degrees, right? So not every continental slope is the same. Okay, and what cuts through those continental slopes typically are canyons. There are canyons out on the ocean floor, and we refer to them as submarine canyons. This is one of the most studied ones off the coast of California, Monterey Bay. This is very deep. This one rivals the size of the Grand Canyon. It cuts really deep, really fast. Okay, it appears that most of them are seaward extension of river valleys. So you can see here, here's a river. You can tell that this river perhaps cut through this area when sea level was much lower. So when sea level was much lower, much of this continental shelf was exposed, and the river just continued along in this way. But now sea level has risen and is continuing to rise. So yeah. And then a lot of these submarine canyons, the reason why they're cut so deep is that they've been cut by turbidity currents. And turbidity currents are like these underwater avalanches. You see that there? This is a simulation of one. Essentially, it's fluid mixed with a lot of sediment, and it moves down slope. And it carries a lot of continental sediment out into the abyssal plain, into deposits that are called deep sea fans. Okay, so it's sediment-laden water. It's almost like an avalanche of material. Okay, and so this is what these are the deposits they create. Huge deep sea fans. Okay, and what happens is as these avalanches move down these submarine canyons, they kind of spill outwards, and the heaviest sediment deposits first, and then the lighter sediment deposits on top of that, and we refer to that as graded bedding. Okay, this is also off the coast of California. Here's the shelf, submarine canyons, and those huge deposits. And so what happens out here is there'll be a turbidity current, avalanche, a lot of sediment deposit, and then there'll be another deposit and another avalanche, another, and they just kind of pile on top of each other. Okay, the rise, the continental rise, you find these only on passive margins, and these are areas where trenches are absent. Trenches are only present in convergent plate boundaries where there's subduction. And when you have subduction, you create a trench, a really low-lying area where sediment may kind of fall into. In a passive margin, there's no trench, so all the sediment just kind of piles up in those deep sea fans, and you get thick accumulations of that sediment. Some continental rises, like the continental rise up the Ganges River, is about 11 kilometers thick. It's all the sediment that's eroding from the Himalayan mountains today being carried by the Ganges River and deposited in the Indian Ocean. So these areas are thick accumulations of sediment. Okay. All right, so those are passive continental margins. Now let's talk about active continental margins. On an active continental margin, you have a continental shelf as well. So you have coastal waters, the same thing, a lot of sediment depositing on these flat kind of areas, gently sloping. And then that bleeds into a continental slope. Again, so very similar to a passive margin, but then what happens is there's no continental rise. The slope goes directly into an ocean trench, okay? And ocean trenches are where you have subducting plate or ocean lithosphere subducting into the mantle. And so that's a really deep portion of the ocean, okay? What you can find in certain active continental margins are features called accretionary wedges. And accretionary wedges are places where accumulations of deformed sediment is scraped off the downgoing plate. I'll show you a picture. Okay, but in some subduction zones, you have very little accumulation of sediment. Okay, so here's a subduction zone. Here we have the continental shelf, and it's hard to see here, but then there's a slope, and the slope goes directly into the trench. So this here is the trench, really deep area. All right, and there's two situations. One, where the subducting ocean lithosphere subducts at a shallow angle. And the reason for the shallow angle subduction is because this ocean lithosphere is very young. And when the ocean lithosphere is young, oh, this is so hard, it's very hot and buoyant, right? So it doesn't particularly, so it means it's not very dense, okay? So the density is very low density, okay? And so that's why it kind of subducts at a shallow angle, okay? And when this happens, the sediment that accumulates on the surface of the ocean plate is kind of scraped onto the continental crust, and it forms this feature called an accretionary wedge. Okay, so that's this feature here, heavily deformed sediment that accumulates here, okay? However, if you have old ocean crust, all right, that means it's very cold, all right? It's cold and its density is very high, okay? High density, which means that the subduction angle will be really high. And when this occurs, then you form a deep ocean trench, right? It's this feature here. There's no continental rise, all the sediment comes down here, and actually the sediment kind of tags along and goes down with the ocean plate into the mantle. Okay, and these areas here are the deepest parts of all of our ocean basins. All right, so here's an example of one. Here's a deep ocean trench. They're very long, narrow features, the deepest parts of our ocean. They're mostly located around the Pacific Ocean, and the reason is because the Pacific Ocean plate is subducting underneath numerous different tectonic plates. And so they're associated with a lot of volcanic activity. And when you have subduction, you'll either have volcanoes that form on ocean lithosphere. We refer to those as volcanic island arcs. And if they occur on continental crust, those are continental volcanic arcs. Okay. Now, if we talk about the deep ocean basin floor, that's the next province of the ocean floor, what we find are abyssal plains. And abyssal plains are like kind of deeper portions of the ocean, not as deep as the trenches, but they're like kind of really flat areas where a lot of sediment, very fine sediment accumulates. You find them in all the oceans. They're very flat, flatter than the state of Florida. Okay, and occasionally what we see on the floor of the abyssal plains are ancient volcanoes that used to be active, typically when that ocean crust was closer to the mid-ocean ridge. Okay, and those are called seamounts and guyots. They're kind of isolated volcanic peaks. And you can see that here. Here are a couple isolated volcanic peaks jutting out of the ocean floor. Okay, many form near ocean ridges or near hotspots. No, I'm not going to spell it. All right, let's go. If we take a look, what's cool about kind of studying the ocean floor, what I've talked about so far is just kind of like the topology of the ocean floor. But if you create an explosion underwater, you can generate seismic waves. And seismic waves are interesting because they'll be able to kind of move past the surface of the ocean floor and reflect off different layers of sediment and then bounce back, and you can collect that information. And this is what a seismic reflection profile will look like. And what the profile shows is distinct layers of sediment, right? And it also shows the basaltic ocean crust and the irregular features of the basaltic ocean crust that are part of the abyssal plain. And essentially the reason why the abyssal plains are so flat is because there's just a huge mantle of sediment that sits on top of it that just flattens the irregular features of the ocean crust that's created at the mid-ocean ridge. Okay, so seamounts can emerge as a volcanic island, okay, and when they do, they're active for a while and they're a volcanic island, that's great, but once the volcanic activity kind of wanes away, then the island is susceptible to erosion, and the ocean always wins. It erodes the volcanic island away and typically leaves kind of like a remnant of that volcano, and that's what seamounts are. And guyots are just flat top versions of that, okay? And they litter the ocean floor. There are over 1 million different seamounts on the ocean floor, okay? All right, the last province of the ocean floor is the ocean, or the mid-ocean ridge. And these are portions of the ocean floor that are at an elevated position. Like I showed you before, that passive margin in the Atlantic Ocean, if you're walking from the abyssal plains of the ocean, you'd be going uphill towards the center of the mid-ocean ridge. And the reason why they're at an elevated position is because they're volcanically active, and all that hot magma near the center of the rift valley, that heat kind of pushes the crust upwards because it's hot and buoyant. Okay, and so what we see is a lot of normal faulting because it has to do with tensional stress, right? So normal faults form as those plates push apart from each other. And you see a lot of volcanic structures in that newly formed crust. So here are some seamounts right here. Okay, this is the ocean floor, and this is mid-ocean ridge right here where new crust is being created. Okay, the mid-ocean ridge, which essentially is like a mountain chain, we didn't know existed until like the 1950s once we started mapping the ocean floor, but they are long features on the ocean floor. There's over 70,000 kilometers of mid-ocean ridge on the bottom of the ocean. It makes up 23% of the Earth's surface. In comparison, all the land on Earth that you can go visit and show off on Instagram or something, that makes up 29% of the Earth's surface. So almost as much land as there is on Earth, there are mid-ocean ridges at the bottom of the ocean. And they wind through all the major oceans, okay? And at the center of them, they have these down-faulted structures in rift valleys where the volcanism occurs. Okay, so here's a cross-section of one. You can see here, there are a bunch of normal faults that form here, okay, and then a bunch of ridges and then kind of low-lying areas here. But then right here is the center of the rift. This is where you have lava erupting on the seafloor, typically kind of pillow basalts that kind of cool down really rapidly as they touch the cold seawater. But here's one plate going in this direction, another plate going in that direction, and here's the asthenospheric mantle kind of moving up, decompressing, melting, and then those melts are kind of crystallizing deep underground and also like injecting their way towards the surface. Okay, so it's mostly basaltic rocks that have been faulted and uplifted. All right, here is the mid-ocean ridge. There are different types of spreading centers or mid-ocean ridges. The mid-Atlantic is referred to as a slow spreading ridge. It spreads at a rate of 2 to 3 centimeters per year. Okay, intermediate ridges, which are in orange, so the Galapagos and the Chile Rise and the Southeast Indian Ridge, they create plates at a rate of like 7 to 9 centimeters a year. Okay, and then the fast spreading ridges, like the East Pacific Rise here, that's anywhere between 15 and 18 centimeters per year. Okay, so they're not all the same. All right, let's talk about some seafloor sediments. The ocean floor is mantled with a lot of sediments, and they are derived from a number of different sources. One is from turbidity currents that just barf out into the deep ocean floor. Okay, it settles basically sediment from the continents. Depending on where you are, the thickness varies. In some places, it approaches about 10 kilometers, like I mentioned, in the Indian Ocean. Okay, the Pacific Ocean, on average, it's about 600 meters or less. And the reason for this is because, I mean, its proximity to land in some areas is pretty far. Also, there's a lot of subduction, so you lose a lot of sediment in that fashion. The Atlantic Ocean has bigger accumulations of sediment. And the reason is there are areas that have been very close to continents for a very long time, where the sediment is mostly derived from, and there's not much subduction in the Atlantic Ocean basin, so it's sediment is allowed to accumulate for millions of years. Okay, mud is the most common type of sediment that forms in the deep ocean floor, and the reason is like if you have sediment sizes that are a little bit larger, they settle out closer to the continental margins, and only the really fine particles make it out to the deep ocean floor. So there are many different types of sediment. The first and most common or most voluminous sediment in the oceans are referred to as Hydrogenous Sediment. That's derived from continental rocks or weathering and mass wasting of continental rocks. And every part of the ocean receives some sort of Hydrogenous sediment. It also includes like volcanic ash when there are volcanic eruptions. All right, and these particles, especially the fine particles, the really small particles, can remain in suspension for a really long time. On average, in the deep ocean, if you have clay, for example, that'll take about 50 years to settle at the bottom of the ocean in the abyssal plains. Okay, and then what happens is the iron in that sediment is heavily oxidized, and that's why the deep ocean, these sediments are usually red and brown colored. The next type of sediment is referred to as Biogenous sediment. And from its name, you can understand that it has an origin in biology, so Biogenous sediment biology. And essentially, they're the shells and skeletal remains of marine organisms. Okay, the most common type of Biogenous sediment are calcareous oozes, and those are organisms that produce their shell or their tests. It's like their armor that they surround themselves with calcium carbonate. And calcium is a dissolved solid in the ocean that's in high abundance. So organisms, we usually pluck that out to create their shells. And when they die, their shells kind of rain down on the bottom of the ocean floor, and they accumulate into these calcareous oozes. There are also siliceous oozes. So some microscopic algae create their shells out of silica. That can accumulate on the ocean floor. So diatoms and radiolarian are an example of that. Those are microscopic marine organisms that kind of float around on the ocean surface. And then phosphate-rich materials can accumulate on the ocean floor, and that can be the the remains of fish, bones, teeth, scales, other marine organisms that can accumulate on the ocean floor. So here's a scanning electron image of some of these organisms. Here's a diatom right here. The colors are false colors. Okay, this is a foraminifera, I think. Okay, then there's a different type of seafloor sediment. There are hydrogenous sediment. And hydrogenous sediment are minerals that directly crystallize from seawater. The most common ones are manganese nodules. Manganese nodules are like potato-sized or golf ball-sized pieces of metal, of manganese, essentially. And the way they form is you need some sort of initial material. It could be like a shark tooth or some sort of cartilage from fish. And then there's a bacteria that actually pulls manganese directly from seawater and deposits around that little structure. And they continue growing over thousands of years. And certain areas of the Pacific Ocean are littered with these little golf ball sized pieces of nodules of manganese metal, which is pretty weird. Okay, scientists don't really understand, like, they sit on top of the ocean sediment, but we don't understand why they don't why they're not buried in a bunch of sediment. They always sit on top, which is peculiar. Okay. Then there are also evaporites. If we have seaways that are narrow seaways that in the past have evaporated away, you'll have like gypsum and salt deposits. Metal sulfides will form in unique environments close to mid-ocean ridges, where you see, I think I got an image here. Yeah, these are vents, volcanic vents at mid-ocean ridges. So what happens is, like, a lot of seawater kind of moves through fissures and cracks on the newly created ocean basaltic ocean lithosphere, and that water will be heated up because it's in contact with like hot volcanic rock, and then you get hydrothermal circulation, and that seawater picks up a lot of dissolved solids, heats up, its density is decreased, and then it kind of flows through other cracks and erupts back at the sea floor at these vents. And these vents are called black smokers because the water that comes out is completely black, looks like a black cloud, and comes out at temperatures of 350 degrees Celsius. Okay, that's 3.5 times the temperature of boiling water. Okay, and remember, this is the bottom of the ocean floor at mid-ocean ridges. The average temperature here is 3 degrees Celsius. Okay, it's very hot. I mean, well, this water is very hot, and this water is very cold. Okay, and so some of these structures can be about like 60 feet tall, and it's basically associated with seawater heating up because of the hot volcanic rocks that are being created at mid-ocean ridges. And then here are those manganese nodules I've been talking about. Okay, so where are these seafloor sediments distributed? You can take a look at that world map. Most terrigenous sediments are deposited very close to the continents, which makes sense because they're derived from continents. The really fine-grained terrigenous sediment kind of makes it out into the deep ocean basin. But in the deep ocean basin, what you find typically are biogenous sediment. Near mid-ocean ridges, you'll find more calcareous sediment because it's at higher elevations. Calcareous oozes dissolve beyond 4,500 meters. In some areas, you'd find siliceous oozes. Okay, and hydrogenous sediment makes up about, it's like less than 1% of ocean sediment. So it's a very small amount. You don't really find huge deposits of this. Okay, and there are very few places on the ocean floor where little sediment accumulates. One example is at the mid-ocean ridges, and the only reason you don't find a lot of sediment there is because it's brand new ocean crust. It hasn't been around long enough to have sediment accumulate on them. Okay, so here you can see, here's the global map. Calcareous oozes essentially deposit anywhere that's in blue. Abyssal clay is here in kind of orange, and brown, which surrounds all the continents, is terrigenous sediment. Okay, and the reason why these areas of the seafloor are important to us is that they provide a lot of energy resources for us. We find a lot of oil and gas on continental shelves, and a lot of northern latitudes we're finding a lot of gas hydrates. That's essentially like frozen methane ice that we find in sediment, and that's an energy resource. We also use sand and gravel and salt for economic reasons, and manganese nodules can be mined. That can be collected and used as a metal.